All right, everyone, let's continue with chapter 11. We're going to do 11:10. So let's just do a quick recap of where we are. Okay, and in section 11.8, we introduced the idea of power series, which are these series with variable x involved. So we have c sub n, x minus a to the power n. We know these things always are convergent at this point x equals a, and they might be convergent elsewhere. They might be convergent on a finite interval around a, or they might be convergent on the entire real line. Okay, and when the power series converges, we can say it's equal to a function, f of x, and that function might be a very familiar function. It might be like e to the power x, or 1 over 1 minus x, like this power series here. And so the power series will be equal to a function on the interval of convergence. So not for all x, but at least for the x's where this power series converges. Okay. And so we started talking about, okay, what functions can we represent as power series? We know that, for instance, looking at this function is equal to this power series on -1 to 1. If I have some arbitrary function like, we'll call it g of x, can I find a power series for this function? And on what interval will it be valid? So in 11.9, we kind of started doing this, right? For a very specific class of functions. We kind of started modifying. We started with the knowledge that, okay, this power series is equal to this function. And then for functions that were similar to 1 over 1 minus x, or that we could get to with some slight modifications, we were able to find power series for those functions, right? So we were able to modify this power series to get power series for functions similar to 1 over 1 minus x. But it's kind of, we don't have many functions that we could do that for, right? What if we wanted to find a power series for something that was very different from 1 over 1 minus x, okay? So that's where we are in section 11.10. What if we want to find power series for more general classes of functions? So we need a more general tool, right? We want to be able to look at a function g of x, and we don't want to have to modify, this power series every time to find a power series for our desired function. So we need to develop a tool where we can take some function meeting maybe some criteria, and maybe just use a, a general tool to find the power series for this function. Okay. So how can we do that? So if we're, just think about the general formula for power series, c sub n, x minus a to the power n. What do we have to work with? Well, we can choose these coefficients, and we can choose this a, right? So the a is just where our power series is centered, okay? So that doesn't make too much of a difference. What we really want to play with are the cn's, okay? If we change the cn's, that's really going to change our power series, right? So the power series is largely determined by these coefficients, these cn's. Okay, so if I want to find a power series for some function f of x, then I really need to choose my CNs wisely. And that's what section 11.10 is. It's all about choosing these coefficients, these CNs, to get a desired power series. All right, so let's try and find, or let's try and determine how we figure out these coefficients to get a power series for a specific function. Okay. So let's say I'm given some function f of x, and I want to find a power series for it. Okay, if f is in a special class of functions, we have a very nice tool to figure out what these cn should be. Okay, so what do we need from f? Let's assume f is infinitely differentiable. Okay, what does this mean? Okay, it means I can find the first derivative, I can find the second derivative, third derivative, all the way to infinity. Okay. So that might seem really restrictive, like, okay, well, that's a very specific class of functions, but this class of functions is actually pretty big, like sine, cosine, all the polynomials, e to the x, a lot of our very familiar functions are in this class. Okay, so we can find a lot of our elementary power series for a lot of our elementary functions using this technique we're going to show. Okay, and let's assume for a second that we already know what the power series for f of x should be. Let's say, I have some general function of excuse me, let's say I have some general function f of x, and I've already found its power series, and I know its power series is c sub n x minus a to the power n. Okay, uh, how are these cn's related to this f? Right. Okay. Well, what do I know about my power series? Right. It's equal to my function on some interval, and maybe that interval is really small, right? Maybe it's just that point A, or we're going to assume it's in a bit larger interval, okay? But we know that this power series has to equal this function exactly when x equals a, right? All right, so let's see what our CNs look like. First, let's kind of write our power series out in long form for a second, okay? The power series is equal to this, right? And then we're saying, okay, hopefully this is equal, we're assuming this is equal to our function f of x. And specifically, we know they're definitely equal at x equals a, all right? So when I plug in a for x, what does the left side become? What does the right side become? Okay, well, the C0 is not affected. And then when I plug a into here, into this term, I get a minus a. All right, that's 0. So I got C1 times 0, which is 0. And then this term will be 0 as well. Okay, and so on. And then what do I get if I plug a into the right side? I would just get f of a. So I have C0 equals f of a. So hey, I've found out what this first coefficient should be, this C0. C0 should be f of a. Now, how can I find C1 and C2 and so on? Okay, so let's see what we're saying. Now we have, let's kind of update our power series. We have f of a plus C1 x minus a to the power 1 plus C2 x minus a squared and so on equals f of a, right? And well, actually, let's see, since I have x's here, let's keep it as f of x. All right, so I have f of a. This is my coefficient. This was, C0, but now I know that C0 equals f of a. All right, so I got f of a plus C1 x minus a to the power 1 plus C2 x minus a to the power 2 and so on equals my function f of x. All right, so now I want to find C1. So what do I need to do? I want to kind of have a similar step in the previous. I want to be able to plug a in and cancel a lot of stuff, okay? But I don't want to cancel C1. I basically want to end up with C1 equals f, I want an expression on the right side that I can evaluate. Okay, so basically what I need to do is I need to get rid of f of a, and I need to get rid of C2 x minus a squared and all that stuff, and I need to leave C1 by itself somehow. So how can I do that? Well, let's see. We're saying that f is infinitely differentiable, and if I look at this is basically just like a infinitely long polynomial, and that's differentiable, right? So I can differentiate both sides. And let's look what happens when we differentiate both sides. Okay, I could differentiate this term by term, right? This is kind of what we developed in section 11.9, that if I have a power series, I can differentiate it term by term. Okay, so f of a is a constant. So what's the derivative of a constant? That's just 0. Okay. And then what's the derivative of this? I got c1 x minus a to the power 1. Well, derivative of that would just be c1, right? Okay. And then let's see, what's derivative of this? I would bring the 2 down and have that, and so on, right? So in general, my derivative would be, if I have the power series Cn x minus a to the power n, my derivative would be n Cn x minus a n minus 1. Okay, so that's what this power series is. So this power series is this power series is this. Okay, and then what would I have on the right side? I've differentiated both sides, so I should end up with f prime of x. Now I have this side equals this side. Let's see what happens again when we plug in a for x. Okay, this term 0. Okay, I have c1 here, and then when I plug in a for x, okay, I got a minus a. That's going to be 0, right? And then every term after that is going to be 0 too. And then I get f prime of a on this side. So what do I see? I see that c1 should be f prime of a. All right. Now let's follow a similar process to find C2, C3, and so on. We're just going to keep differentiating. Okay, so let's again start with our equation here. What do I got? I got C1 plus 2 C2 x minus a plus 3 C3 x minus a squared plus blah, blah, blah equals f prime of x. Okay, so in series notation, this left side is equal to n. Okay, now let's differentiate again. Okay, if I differentiate again, okay, this is a constant. Oh, and we can be specific. We said this C1, we now know C1 is equal to f prime of a, right? Okay, but it's still a constant. So when we differentiate a constant, okay, that's going to become 0. When we differentiate this term, we get 2c2, okay, no x's. We differentiate the next term, I get 3 times 2 times x minus a to the power 1. The next term would be 4 times 3 x minus a squared, and so on. And that should equal f double prime of x, right? Okay, and writing this left side in series notation, it would be n times n minus 1 Cn x minus a to the power of n minus 2. All right. And then let's plug a in for x again. And what do we get? Okay. Well, this term is 0. This term would be 2c2. This would be 6 times 0, which is just 0. The next term would be 0, and so on. And then on the right side, I'd have f double prime of a. So I see that 2c2 should equal f double prime of a. So now I can solve for c2, right? c2 should be equal to f double prime of a over 2. Let's do this one more time and we should see a pattern start to emerge, okay? So let's write our second derivative of our power series again. Okay, so this is our power series for our second derivative. Okay, I got f double prime on the right side. On the left side, okay, I got 2. I should have 2 times 1 c2. But since I know c2 is f double prime of a over 2, I've just written this in place of c2. Then I have 3 times 2 c3 x minus a to the power 1, and so on. That's the same as this line here. Okay. So now my goal is to try and find c3. All right, so let's differentiate this again. Let's follow our same pattern. I take the derivative again. Okay, on this side, I should end up with the third derivative of x. And what should I get on the left side? This is a constant, so it goes to 0. Here, let's see, I should have 3 times 2, which is just 6. C3. Okay. And then the x disappears. The next term should be 4 times 3 times 2. C4 times 0. Okay, so actually this term should go to 0. Well, actually, before we plug in a for x, let's just write out what it should be. This should be 4 times 3 times 2 C4 x minus a to the power 1, and so on. Okay, and that should be equal to the third derivative of f of x. All right, and now again, okay, let's so we can write out the power series notation. So the power series is getting a little complicated here. It's not too important. I'm just writing it down for reference. Now let's see what happens when we plug in x equals a. Okay. When I plug in x equals a, let's see, 6c3 is not affected. This term, when I plug in a here, that's going to be 0. So we're going to have plus 0. All the other terms are going to be 0. I get f triple prime of a over here. All right. So I got 6c3 equals, okay. The higher derivative I take, the more of a pain it is to write, if I want to take the 8th derivative, I wouldn't want to write 8 hatch marks, right, for the 8th derivative of f. So how I can represent the third derivative of f is I just write f and then a 3 in parentheses up here. The parentheses mean we're taking 3 derivatives, not f to the power of 3. Okay, so this is notation we need to be familiar with. So I have 6 times c3 equals third derivative of f at a. In other words, c3 equals this. Okay. Now let's see if we can spot a pattern. I'll write down all the information we have. We found out that c0 equals f of a. c1 equals f, the first derivative of f at a. By the way, if we have f of a, we can write that as like f0 of a, meaning we're taking 0 derivatives of f, we just have f itself. C2 is equal to the second derivative of f over 2. Okay. So second derivative of f at a divided by 2. C3 is equal to the third derivative of f at a divided by 6. So in, let's see, in these first two entries, we can consider these both over 1, right? Same thing. So we got fractions. Let's see if we can spot a pattern. We got 0 derivative, first derivative, second derivative, third derivative. Okay, so that's pretty obvious. We can see Cn should be equal to this thing where we have, okay, nth derivative of f at a, right? What's going on with the denominators? Okay, I got 1, 1, 2, 6. What does that remind you of? This should be familiar, hopefully, as the factorial. Okay, 1 is 1 factorial. Okay, 2 is 2 factorial. I'll keep them as fractions. Okay. Okay. 2 is 2 factorial. And 6 is 3 factorial, right? I got blank over 3 factorial. How does this first term compare? Okay, maybe you guys don't know, but 0 factorial is not 0. It's actually equal to 1. Okay, so a little weird fact. If you guys are interested, I can explain that to you in office hours. It's a pretty intuitive explanation. If you don't want to bother with that, just remember that 0 factorial is not 0, is equal to 1. Okay, so what are my denominators? 0 factorial, 1 factorial, 2 factorial, 3 factorial. I expect it to continue in that pattern, 4 factorial, 5 factorial, and so on. So the denominator of the Cn should be n factorial. Okay. So I've figured out a general formula for my CNs. If I'm saying that f is infinitely differentiable and it's equal to this power series, okay, on some interval, then the form of these CNs, these CNs have to be a very specific form. They have to be exactly the derivatives of f at a over n factorial. All right, so let's just recap what we know. Okay, let's say I have an infinitely differentiable function, and I know it's equal to this power series on some interval. Okay, then I know exactly what the CNs have to look like. They have to be the derivatives of f at a over the factorials. Oh, I can write this a bit clearer. Okay. So the power series would look like this. And this power series where we have the coefficients are determined by the derivatives of our function f, there's a special name for this. This is called the Taylor series of f centered at a. Okay, so this is where the title of the section comes from, Taylor series, and this is important terminology to know. Taylor series refers specifically to something like this. Okay, now what did we say a second ago? We're saying f is infinitely differentiable, and we're assuming it's equal to this power series. That's not a trivial assumption. Okay, it's not always going to be the case that f is going to be equal to this thing. All right, we would really like it to be, right? It would make life easier if all we had to do was find the derivatives and we had our power series. It's not always the case. You might think of it's sort of once we get a bit further, you might think of it as nitpicking a bit, because pretty much everything we're going to see in this course, every function we see, if we make its Taylor series, it's going to be equal to its Taylor series. But it's not. There are some counterexamples. Okay, so this maybe what I'm saying is kind of logically complicated. So let me just reiterate. If we have an infinitely differentiable function and it's equal to this power series, then the power series has to have this form, okay, where the CNs are the derivatives of f over n factorial. Okay. Now, if we have, let's say we just have an infinitely differentiable function f and we don't know it's equal to a power don't know it's equal to this power series, we can still make this power series from the derivatives of f, right? We can still we have this function f, we can still construct this power series over here, this Taylor series. We can still make this thing, right? We can still make a power series with these coefficients. We would still call it the Taylor series of f centered at a. We just don't know that it's equal, okay? So we can always make this thing, but we don't know if these two things are equal or not. Okay, so there's a special way to determine if they're equal. We'll get into that later. But what I want to drive home to you guys is that if f is infinitely differentiable, we can always construct this power series, okay? This Taylor series for f centered at a. So let's see an example real quick. And then I'll show you another justification for why this works. Let's say our f of x is equal to e to the power x. All right. Let's try and let's make the Taylor series for f centered at 0. Centered at x equals 0. Okay. So let's see. What do I need? I need to know the derivatives of f, right? Because my Taylor series is going to look like this. Let's see, I'm centering it at x equals 0. So my a is 0. Okay. And then I have x minus a. So again, x minus 0 to the power n. All right. So all I need to finish my power series for e to the x are these derivatives, okay, of e to the x. Well, what do I know about the derivatives of e to the x? Okay, f prime is e to the x, f double prime is e to the x, f triple prime is e to the x, and so on, right? And then what are the values of these when x is equal to 0? They're all equal to 1, right? Okay. So my Taylor series for e to the x is 1 over n factorial x to the n, which I could simplify as x to the n over n factorial. Okay, so in previous lecture videos, I used this as an example of a Taylor series for power series for a function, and now we see where this comes from. It's from this Taylor series. I'm just taking the derivatives of my function e to the x, evaluated at 0, and then they're multiplied by this x to the power n, and I end up with this, x to the power n over n factorial. Now, I haven't answered the question of does this power series equal, or excuse me, does this Taylor series equal the function? Okay, so that's still something to determine. But we can at least say that this is the Taylor series of e to the x centered at 0. We don't necessarily know if that Taylor series equals the function or not. Just a note that the center of our the formula is the same for different centers, different choices of our center A, but it can make our power series look quite different. So let's say we have where our f of x is e to the x again, but we want to find the power series for it, or the Taylor series for it, centered at, let's say x equals 2 is fine. Okay, so how would we do that? Okay, the formula is still similar, but let's see, it should be f to the n of 2 over n factorial x minus 2 to the n, okay? So maybe it won't look as clean. Instead of having just x to the n, we have x minus 2 to the n and so on. But it follows the same formula. We need to find, let's see, the only thing we need to find, we got n factorial x minus 2 to the power n. There's nothing to do with those. All we need to do is find these derivatives of f and then evaluate them at 2. So again, we know f prime is e to the x, f double prime equals e to the x, and so on. Okay, and then we evaluate these at 2, and we could just leave them as e squared. We don't need to find the decimal form of this. Okay, so all of these would be e squared. Instead of 1, we have e squared. Okay, so my power series would look like this. My Taylor series would look like this. Okay, so it can make our power series look very different though. So the previous one, when it was centered at 0, it has this nice compact form, and when it's centered at 2, it has this slightly more complicated form. All right, so the choice of our center can affect the way our power series looks, but it's the same formula. So now I just want to give a kind of graphical argument of why the power series for f, okay, again, we're kind of assuming a lot by saying they're equal, but why should the power series or the Taylor series of f centered at A look something like this? Okay, so let's kind of consider this just quick graphical example. Let's say I have a function f that kind of looks like this. I'm just drawing it like this so it's easy in the long run. Okay, let's say I have a graph like this, and I want to make a power series, a Taylor series for f centered at A. Okay. We could think of a Taylor series as an approximation to our function, and the approximation, if we have an infinite amount of terms, the approximation is so good that hopefully it's not even an approximation anymore, it's exactly equal. But let's kind of build up from something that is an approximation. Okay, so let's say I have this function f of x. Let's try and approximate it, and let's consider like trying to approximate it kind of on a fixed interval here. Okay, how can I approximate this function on this interval? Okay, maybe the first approximation I could do is I could just say, okay, well, I'm going to say that everywhere, let's see, my approximation on this interval is I'll just say that f of x is about equal to f of a everywhere on this interval, right? So I just have, if I think about what f of a, I could say f of a is equal to a function, but it's like a constant function, so just a flat line. So I'm using this flat line to approximate my function f. And in some places, that's a pretty good approximation, right? Like if I'm looking at this point here, let's call it xo. If I'm looking at this point xo, this line is a pretty good approximation to this function. And maybe over here, it's not as good, but it's still pretty good. It's better than, some line way down here, right? So this is a pretty good approximation. How can I make this this approximation better? What if instead of a flat line, what if it had some slope to it? Okay, so I could have a lot of lines with slope, right? Maybe I have a line going like this through xa, or maybe going like this. So some of those maybe are better than others. So what's the best choice of slope I could pick? Well, let's say I want I want to keep my power series centered at A. Okay. We want our approximation to be best at A. Okay, so we want our approximation to be best right here. Okay, so if I want to pick a line with, some other slope, let's kind of get rid of this flat line. Oh. Okay, so if I wanted to draw a line through this point with some slope, what slope should I pick? Well, how about the same slope as the function has at this point? So what is the slope of the function at this point? Well, that's the slope of the tangent line, right? The value of the derivative of f at a. So I should have a line, let's see, the slope, maybe it's still pretty flat, but maybe the tangent line looks like that, right? So maybe I should have this be my approximation. And yeah, maybe we see this is a bit better approximation than our previous flat line. Okay, so we could say f of x. So what's the equation for this line? Well, if you use your algebra knowledge, the equation of this line should be, it's passing through this point a f a. The equation of that line should be f of a plus f prime of a times x minus a. Okay. Now this is starting to look like, we can see this first, these first couple terms are already starting to look like our power series, right? So if I wanted to make this approximation even better, what should I use instead of a line? Maybe I should use a parabola. Okay. So I get, if I wanted to approximate this graph with a parabola, I'll try and erase this and draw a parabola. Okay, I've kind of drawn a couple different approximations here. Let's say this black parabola is my I would call this like a quadratic approximation of my function. Okay, that parabola is an even better approximation to my function f. And what would the equation of that parabola be? Well, it turns out it would be again, very similar to our power series. The equation of that parabola would be f of a plus f prime of a x minus a plus f double prime of a x minus a squared. Okay. Then if I wanted my approximation even better, I could use a cubic instead of a quadratic, and I could say f of x. And as you might guess, it just follows the expansion of my power series. It would be this, and so on. And the idea is that as I take more and more terms going to infinity, the thing, the this can think of it as these polynomials. These polynomials should end up being exactly my function. So if I take an infinite amount of terms, it should end up being exactly my function. Oh, and you know what? I'm missing some coefficients here. This should be divided by 2. This should be divided by 2. This should be divided by 6, and so on. Okay. Um, so this is kind of a quick and dirty graphical justification for what we did analytically a while back. Okay. And I just realized, these coefficients are still wrong. It shouldn't be. It should be 2 factorial, which is 2, and then this 6 is, this factorial is redundant. It should be over 6, or I could write this 6 as 3 factorial. Okay, but I'll leave it as 6. All right, so this is finally correct. Okay. Moving on. The graphical example I just showed, it kind of segues nicely into our next topic. When we have a infinitely differentiable function f, okay, like I said, we can always make this Taylor series centered at a. Right? We can always make this thing, but then we have the question is, we have the question is are these things actually equal? Okay, so we don't know this. All right, so we're gonna segue into figuring out when does f of x equal its Taylor series. Okay, to do that, we need a little machinery. Okay, so before we consider the Taylor series from 0 to infinity, let's consider something finite. Okay, so let's say n equals 0 to k of this. Okay, this is a Taylor polynomial, and let's just write out what would it look like. It would equal f of a plus f prime of a, x minus a, and it only has a finite number of terms. It goes up to f k of a, x minus a to the k over k factorial. So this is similar to these approximations I was talking about in the previous slide. Okay, we said f of x is about this polynomial. Okay, so this thing has a special name. It's called a Taylor polynomial, just like the Taylor series. This is the Taylor series going from 0 to infinity. If we just cut it off at a finite k, we call it a Taylor polynomial because it is just a polynomial, right? These are coefficients, and then we got powers of x. Okay, so this thing we call the Taylor polynomial. Now, what we're doing with our graph, we were using these Taylor polynomials to approximate our function f. We said f of x, all right, it should be about our Taylor polynomial. Okay, f of a plus f prime of a, x minus a plus dot dot dot. We said it should be about equal to that. All right. So this right side is an approximation to our function f. Okay. So we could talk about how good that approximation is, right? We could say, let's call this thing. Let's give it a name. Let's call it. We could call it Tn of x. Okay, meaning this is or let's call it tk of x. Okay, so this is the Taylor polynomial. This t stands for Taylor polynomial. This is the Taylor polynomial of degree k, meaning the highest power of x should be k. Okay. So we can talk about the error of this approximation. Okay, we could say f of x minus the approximation, this Taylor polynomial, that should give me an error, right? So let's call that rk of x. And in this case, instead of talking about error, let's call it remainder. Okay, so this rk stands for the remainder. We subtract the Taylor polynomial from f and we get a remainder, right? And we'll say it's rk of x, meaning the remainder when we subtract away the kth order Taylor polynomial. All right, so if the Taylor polynomial becomes a better and better approximation to our function f, this remainder should be getting closer and closer to 0, right? And that's what we mean when we say the Taylor series is equal to the function f. It means, okay, if I cut off my series at k, and then I have this remainder rk, if I make k bigger and bigger and bigger, the remainder should go to 0. That's what we mean. We can state this formally in a theorem. So I'll write out a theorem real quick. It'll pop up in a second. Okay, so here's the theorem. I'll read through it and then kind of explain it. If f of x equals t sub k of x plus r sub k of x, where t sub k of x is the kth degree Taylor polynomial of f centered at a, and the limit of rk of x as k goes to infinity equals 0 for x minus a is less than r, so distance, absolute value of x minus a is less than r, and here r is r is a real number, then f equals the sum of its Taylor series for absolute value of x minus a less than r. Okay, so what does this mean? So we're taking our kth order Taylor polynomials. We're taking, we're just cutting off our Taylor series. Instead of going to infinity, we're gonna just let it be a Taylor polynomial that goes up to k. Okay, so that's what tk is. Okay, so at each step, we can always say that f of x equals tk of x plus rk of x, right? We can always say this, but maybe the remainder is really big, and maybe it's always really big. Okay, but what this theorem is saying is that if we write f of x like this, its Taylor polynomial plus its remainder, and the remainder goes to 0, the limit of the remainder goes to 0. All right, so meaning if I take a larger and larger degree polynomial, the remainder is getting smaller and smaller and smaller, then f is going to eventually equal the sum of its Taylor series, meaning if I, instead of taking k terms, if I take an infinite number of terms, then f is going to be exactly equal to its Taylor series. So if the remainder goes to 0, then we can say f of x is equal to exactly its Taylor series on this interval x minus on the this interval x minus a is less than r, so the interval would look like a minus r to a plus r, and maybe we have to check the endpoints again, but we can definitely say it's at least equal to its Taylor series on this interval. All right, so we'll have f of x is equal to exactly the Taylor series. Okay. So that's the distinction between function being equal to its Taylor series and just having a Taylor series, right? We can always, if f is infinitely differentiable, we can always make this Taylor series. We can always construct it, but the two won't necessarily be equal, right? So we're asking, are they equal? And now we have a condition that tells us when they are equal. Well, they're going to be equal when the remainder goes to 0, when I consider like a finite number of terms. Okay. So that's our condition for having equality here. Now, there is a tool we can use to actually prove in this class. Like I could give you a function e to the x, and I could give you a problem that says, okay, and I could give you a problem that says find the Taylor series for e to the x centered at 0. And I could also give you a second part of the question that says prove e to the x equals its Taylor series. Okay, so how do we do this? We've seen what the condition we need to show. Okay, we need to show that the remainders go to 0. How can we do that? It's a bit of it. It has been required in this course in the past. I'll hold off. I won't put it in this video, and I'll double check to see if it's going to be on the final. If it's on the final, I'll make a special video for it. I think it's kind of a little bit complicated for this level of course. So I'll double check. So keep an eye out for that if it does end up being required. Just a couple notes before I end this lecture. Okay, let's kind of recap. Okay, so here's our recap on the Taylor series section. If f of x is in the special class of functions, these infinitely differentiable functions, we can always make a Taylor series for f. Okay, so the Taylor series is just going to be these derivatives, the derivatives of f at a over n factorial, x minus a to the power n. But f of x might not be equal to its Taylor series. They should always be equal at the point x equals a, but maybe it's not gonna be equal on any kind of interval. Okay, so that's what I mean here. If f of x is equal to its Taylor series on some larger interval, we say that f of x is analytic. Okay, that's just a technical term meaning our function f has a power series representation and it's equal to that power series representation. Okay, we can choose different centers for our Taylor series. We saw an example earlier. We could have centered our Taylor series for e to the x at x equals 0 or at x equals 2, I think is the other case we showed, but we could pick any center. But when our Taylor series is centered at x equals 0, that's a special case, and we give it a special name. We call it a Maclaurin series. It doesn't change any of the properties or anything. It's just that these usually have a nicer form, and so we deal with them so often that we give them a special name. We call them Maclaurin series. So if you see that terminology, don't be freaked out by that. It's the exact same. It is a Taylor series. It's just the special case when we're centered at, this should be, when our center A is 0, okay? No other notes for this section. Obviously, the problems in this section are kind of complicated. This is all theory. I will make a problem video for this section so you can see how these are worked in practice. Hopefully you all understood that. Let me know if you did not.